at Texas A&M with high performance research computing. And today we're going to go over using the Slurm scheduler on the ACES cluster. So here are the topics that we'll cover today. I'll introduce or go over HPC architecture, how the compute nodes and login nodes are connected and related. We'll go over some common SBATS parameters that you can use in your job scripts, and then we'll look at some example job scripts that can run on that are designed to run on a single node, and we'll look at some how to reconfigure this to run on multiple nodes. Also, depending on the software that you have, it may only support running on a single node, and it may only support running a single core, but it may also support running multi-cores. So we'll go over those too. We'll look at, for multi-node jobs, we'll look at using how to schedule or how to configure your Slurm parameters for an MPI job. And we'll go over the tamulauncher, which is a way to launch multiple single core jobs across multiple nodes. And then we'll submit a job script and we'll monitor the resource usage at runtime and after the job is completed. And we'll look at some common job failure issues and how to debug these. And then we'll look more into job details. So this is an image of the ACES cluster. It's a Dell cluster, and there's a number of accelerators attached to multiple nodes. So we have the PVC. Those are the Intel Max GPUs. There's Intel FPGAs. There's NVIDIA H100s and A30s. And a lot of times this software you have may or may not support each of these accelerators. So you'll have to read the documentation and maybe compile the software a specific way so they can run on any of these accelerators. All right, so we're going to log into the ACES portal, and you can access the portal from our main website, hprc.tamu.edu. Go to the portal tab and then go down to ACES portal for access users. So the first time you log in, portal, let's go back to portal, ACES portal for access users. So the first time you log in each day, you'll have to use your access ID to log in, and you'll see an image like this or a web page like this. You can select your access ID. There's a drop-down box here, or if you're registered using your TAMU ID, there's also an option for TAMU. So select your access ID and then click log on, and it'll take you to the logon page where you enter your access ID and your access password. All right, so let's go ahead and if you haven't done so, log into access portal, the ACES portal, using your access credentials, and just give us a thumbs up if you've connected. It just in your chat, you can let us know that you've connected to the portal, so we'll know how many users we have working on the ACES portal. All right, we have one person connected. And when you connect, you'll see this ACES logo, and you'll see the portal menu. We'll give everyone just another minute to connect. Someone else is connected. All right. Have another person connected. If you need help connecting to the portal, you can leave a message here in the chat, or if you want to unmute yourself, you can ask a question. All right, we're going to go ahead and move on. So log into the ACES portal, connect to the shell command line, and then what messages do you see on the command line? So I'm already connected to the portal. Select clusters, ACES shell access. Now you're at the command line. So you're actually on a login node. We'll cover login nodes and compute nodes, and I'm on login node number 3. So if you want to just just post in the chat which login node you landed on. So to get to the portal, it's portal, go to our main webpage, hprc.tamu.edu, mouse over portal, and then select ACES portal access. We'll be using ACES today. And when you do that, you will, if you haven't logged in for the day, you will reach the access login page. You have to have already an access ID, and you'll have to have it configured for dual authentication. All right, so now we have, see, some users are logged into login 2, and some are logged into login 1, and I'm logged into login 3. This is just a way that the cluster distributes the workload across login nodes. If we had 3 login nodes and everyone was on login node 1, that's not an efficient use of resources, since we can spread the load across multiple login nodes. All right, so if you log in again later today or tomorrow, you may land on a different login node. But for the most part, your files are, or you can access your files from any login node. So whichever login node you land on, it doesn't really matter. All right. All right, so node, I'm using the term node. What is a node? A node is a computer unit, one computer unit of an HPC cluster. Each one of these units contains memory and multiple CPUs. We've got 2 types of nodes. We've got the login node and the compute node. You can see your prompt shows you you're on login 3, so you're on login node 3. The compute node, those have different types of names. We'll see what those are in a little bit. The login node is where you first log in and you create your job scripts. It's just a text file, so you use your favorite editor, VI, or you can use the portal. There's an editor in the portal, and this is where you can practice using the software and running Unix commands. So compute node, this is where all of the processing, the main processing is done. These are we often call these just nodes. Even a Slurm parameter is called just nodes. And jobs are only scheduled on the compute nodes. So some compute nodes contain GPUs or the other accelerators that we mentioned, and some compute nodes are CPU only. So based on how you configure your job script, you can use one compute node or multiple compute nodes, but just remember this is highly dependent on how the software is written and what it supports. Cores. So on the ACES compute nodes, each one has 96 cores. These are also termed CPUs, and sometimes you'll see the term threads being used. The ACES compute nodes have 512 gigabytes of memory. Some of this memory is allocated for the operating system on the compute node and other resources. So you have 488 gigabytes of available memory. So you can use one or all 96 cores in a job script. Just be aware of the software you're using. If it only supports a single core usage, then you only need to request one core. But if your job script does, if your software does allow you to specify the number of cores or threads, most likely it will get completed faster if you use the entire compute node, all 96 cores. Just be aware that sometimes, even though software only supports a single core, it may use 300 gigabytes of memory. So in the end, you may have to just go ahead and use the entire compute node. All right, here's an example of how an typical HPC is configured. We have the login nodes here in gray on the left, And this is, like I mentioned earlier, this will do file manipulation and JavaScript preparation. You can install your software and do some light testing. This is for short tasks, less than 60 minutes, and you will need to, any testing, you will need to limit it to 8 cores on the login node. Now, we do have scripts in place that if you run any tasks that once they reach 60 minutes, they will be automatically stopped. So just be aware, this is for short testing, and try not to use up all the memory on the login node, because that will slow down the performance for other users that are trying to edit their job scripts. You know, the login nodes are connected through a local network to the compute nodes. And this is just an example. We have hundreds of compute nodes, and each of these login nodes and compute nodes share the same file storage. So anything you create on the login node can be accessed on the compute node, and vice versa. Any output that's generated for jobs on the compute nodes, you can review this from the login node. Compute nodes, use those for jobs lasting more than 60 minutes. And then we'll show you how to configure the job scripts to use the entire compute node later. So ACES is a composable cluster. And what I mean by composable is that accelerators like GPUs or FPGAs are not directly connected, or SSDs that are not directly attached to each compute node, as in this gray box on the left. This is the traditional server configuration where you have a server with one, and then the top image here has one GPU and one SSD installed. The second image down has 2 GPUs attached and 1 SSD installed. So these are pretty much plugged into the server itself. So all the hardware is connected within the server. So if you use this compute node, you're limited to only 2 GPUs and 1 SSD. With a composable cluster, what you can do is we have this connectivity called the liquid fabric. So we have a pool of servers, and then we have a pool of accelerators and a pool of storage and memory. So these are not connected directly, but through this liquid fabric, you can schedule a job to run with one server and have 4 GPUs connected and an SSD, for example, in the second image. Or if you have software that supports 14 GPUs, like in this this bottom box here, this bottom server diagram, at runtime, you can schedule your job script with 14 GPUs. In the case of the traditional server on the left, these would have to be manually plugged in to the server if you wanted to use 14 GPUs. All right, here's an example job script. It's just a text file. When you create your job scripts, the first line will always be exactly like this, with no spaces after the bash word here. So these are Unix commands. Anything that begins with a £, that is recognized by Unix as a comment. Slurm is looking for sbatch parameters that begin with £sbatch, no space before this pound. So £sbatch space, and then Slurm is going to look for parameters for each line that begins with £sbatch. These are the common parameters that are used. The job name. Just keep it simple, short and simple, because when you're querying what your jobs that are running, the job name field is limited to a certain number of characters. So make the first few characters more descriptive if you have multiple jobs and you want to see which job is at which stage in the running process. You can also use quotes if you need to use spaces. You can also put comments after each of these lines, but don't put anything after the bash line. Time, this is the max time. that you want to allow your job to run. If you're familiar with the software and it usually takes about 12 hours to run, you can go ahead and schedule it for 1 day. This is the format, 1 day, and then you've got plenty of time in case that job takes 14 hours. Then the number of nodes you want to use, and there's a number of different ways to configure how many tasks on each node. This is a descriptive way of seeing it. Number of nodes, specify it for 1. Number of tasks per node. I'm going to run 1 task per node. A task is like a command. So I'm running 1 command on 1 node, and that command will use just 1 CPU. So this is, and the memory of 5 gigabytes. So this is for a software or a command that's not going to require a lot of resources. And then you have a standard out and standard error files that can get generated at runtime. So these two are good to use. You can name them whatever you want. This %x and %j will just append the job name and the job ID. It's important to append the job ID so that you can associate the job ID with the standard out and standard error files. So again, comments here begin with the pound. You'll want to do a module purge. That's a good practice before you load any modules. We recommend putting a module purge line in there. Then you load your modules before you run your software. And okay, I've covered all these. When you name your job script, you can name it whatever you like. Just be consistent. It'll help at a later time when you're trying to search for all of your job scripts. You can use a wildcard with .job if you've named all yours .job or .slurm. All right, some of the commonly used SBash variants. We saw nodes. You just change the number from 1 to the maximum allowed, and we'll see what is the maximum allowed for each. For the type of job, we'll look at that later. So with nodes, this can be used with in tasks or in tasks per node. You want to let Slurm know how many tasks you're going to run on each node. In tasks, this is the total task across all nodes. Again, there's different ways to configure a job script. If you use in tasks and you want to run your software across many nodes, then you'll have to do the math and figure out how many total in tasks you're going to run, and then you also include in task per node to let Slurm know how many in tasks per node. Also, CPUs per task can be used. This is an example on the right. It's just a command for a software called Spade. It's a Python script. This would be an example of a task. It's just the command that's used. And then CPUs per task is in this case, there's an option in the Spades application called threads, and you can specify the number of threads. So you want to match this number of threads with the CPUs per task that you selected in your job script. All right, time. Here's the format for time. You can use, you can start it with hours. You can configure it with days. Makes it a little easier than trying to multiply 24 by the number of days. Memory, just specify with capital G, and we'll show you how to identify the maximum amount of memory on a compute node that you can use. And this is a total memory for each node. This isn't total memory. If you select multiple nodes, this is not the total memory for all nodes. It's just for each node. Job name, we went over that. Output and error, we went over that. Partition, for certain compute nodes, you will have to specify the partition. We'll show you that in a little bit. But this would include the GPU partition, the PVC partitions. Otherwise, if you're not going to use any accelerators, you don't have to include the partition parameters. it will automatically be set. All right, GRES, this is the way you specify the type of GPU to use. This is you can use the GPU eval command to see the types of GPUs we have, and we'll go over that in a little bit. So the parameters -- gress equals GPU colon the type of GPU, H100 or A30 as we have on ACES, and then a colon, and then the number of GPUs. And then if you do want to use a GPU, you have to specify partition GPU. Because we have GPUs in more than one partition, so you need to specify GPU or GPU_debug partition. And those partitions are different, and we'll go over that in a little bit. Okay, account. This is for your service units account, your project account. By default, you have one account that will be set in your My Project command. So if you run My Project, see, I have one account. It's for fiscal year 2025. This is my account number. Make that look. Okay. So this is my account number for fiscal year 2025. It is set as the default account. If I have several accounts, only one will be set as the default, and you can change that. Just run the My Project -H to see the help, see how to change that. Right now I have 1,000 service units. There are none that are used or pending, and my balance is 1,000. So you can change your account with -D. You can do that a single time right here, or you can do that within your job script with the account parameter. Just give it the account number you want to use. You can specify an email address and the type of email you want to send. You want the cluster to send you. If you want any type of event to be sent to you, you can use all as a mail type. If you want to just use end, then it will only send you an email when it ends. Otherwise, you'll get one when it begins and one when it ends. And if you configure too many jobs running at the same time, and each one of them is sending an email at the beginning and end, you're going to get a lot of emails, more than you need. So just be careful when using this parameter. Here's another useful parameter, dependency. If you want to run one job and then you want to run a second job only after the first job is completed, you can add this dependency equals. The option is after OK, and then a colon, and then the job ID of the first job you submitted. So after you submit your first job, get the job ID with this command squeue-me, get the job ID, and then configure your second job script with the job ID and this flag. And remember, #sbatch goes in front of all of these -- parameters. All right. We went over the first couple. So you submit your job script from the command line. And the start time depends on the available resources. Fourth point here, you use the sbatch command and the name of your job script. And then once you run this, it will put your job into a pending state until resources are found. And you can submit a job on the command line a different way, or you can start an interactive job with the srun command. This is good for interactive, where you have to input. Maybe you have to view intermediate files before you run the next command. But if you know all the commands to run your job, it's good to have a job script. That way you have a history of the commands that were used. All right. We saw the term partition earlier. Compute nodes are assigned to a partition, one or more partitions. A partition can have certain attributes. For example, an accelerator attached, or maybe there's a different short or a long runtime associated with a certain partition. For example, we have the GPU queue that has a maximum runtime of a certain number of days, but we have a GPU debug queue that has a maximum runtime of just 2 hours. Some of these you have to specify the partition flag, others you don't. Run the sinfo command to see the partitions. So if you go to the command line, run sinfo, you can see the partitions. You can see the GPU has a max of 2 days. GPU debug has a max of 2 hours. All right, so a queue, this is a list of scheduled jobs. The jobs can be in a pending state, they can be in a running state. They will be in a completed state for just a few seconds. So you'll rarely see the completed state in the queue. This is the queue. It includes all the jobs from all the users and all the partitions. You can narrow it down and see just a specific queue. CPU queues is auto assigned. We went over that, but you must specify the GPU. All right, so we did the sinfo command, and that gives you some information of the time limits. You can also see the maximum number of compute nodes that you can configure in a job script. For example, the CPU partition, you can configure up to 64. You can configure up to 64 nodes on in your job script. But for the GPU partition, the maximum is currently 8. I'll go over how to look at least the GPU queue so that you can schedule your job based on the GPUs that are available. I'll go over that in a little bit. Some of these queues are not available to all users, for example, the staff queue. And you can see that the nodes AIOT, A is active and used by running jobs, I idle, O offline, T total. So active 43, there's 0 idle, there's 11 offline currently, maybe due to maintenance or rebooting, and we have a total of 54 in the CPU queue. GPU, we have 5 nodes in this queue, or sorry, 7 in this, the GPU partition, and then 3 in the GPU debug partition. You can also look on our main web page. In the left side, we have a breakdown of each of our clusters, and you can see how busy is the cluster. For example, the ACES cluster, 51% of the nodes are in use. Shows you how many jobs are running, how many are queued. In this case, there's a lot of jobs queued in this example. All right, so the GPU avail command, let's say you want to run a job on a GPU, but you're not sure if the H100s are available or the A30s are available. So if you run this GPU avail command, this will show you what is configured, which this can change over time since this is a composable cluster. You may see eight H100s on a node, or you may see 5 or 6 H100s on a node, or in this case, we have 15 nodes that have 2 H100s attached. So if your software, if it doesn't matter whether you want to, it doesn't matter which GPU you want to use of the NVIDIA GPUs, H100 or A30, you can run this command to see what's available. So GPU avail, you can see currently we have, there's a lot of PVC nodes, but your software needs to support the PVC architecture before you should actually use those. You can see the configuration. This is what's configured and this is what's available. So if you wanted to run an H100 job, unless this node is being held for some other job, you could schedule it right away on this H100. or there are both of the there's two A30 nodes, and both of these are available right now. Okay, so that's useful if you want to run a H100. You want a job using H100, but can use A30, and if there are no H100s available and there's A30 available, then you can reconfigure your job script before you submit it. All right, to look at the maximum number of cores and memory available for any of the partitions, you can use the max config command. This command will default to the CPU partition. So if you want to see the maximum for a GPU partition or any of the other partitions, you will need to specify the partition name. But just running it with no options, the default will give you the CPU, the maximum CPU resources that you can configure. For example, the maximum runtime is 7 days on the CPU partition. The maximum was 64 nodes, which we saw earlier. That comes from the sinfo command. So there's also a note here that tells you there's 64 for the CPU. If you were to run GPU, you would see a different max and a different max runtime. CPUs, the max you can max CPUs per task is 96. There's 96 cores on the node. The max amount of memory you can configure is 488. If you configure it with 500 or 512, for example, there aren't any nodes that have 512, even though the nodes are termed to 512 gigabytes of memory. Only 488 is usable, and there aren't any that have 512 gigabytes of usable memory. All right, so let's look at the max config command a little more. So max config -H. This shows how you can be very specific in what you want to view. We saw the default was just the CPU partition. Let's just say you want to let's say you want to see what the max config is for the GPU debug partition. The partition is GPU debug. Here is the maximum. Now, actually, this is not correct. I got PVC in here. All right, that's a bug there. While the PVC is showing up in GPU, I have to fix that. If you just run the max config, it will show you for the CPUs. It's at 64 cores, 96. For the GPUs, I'll have to fix that. We've got a lot of PVC nodes now. Oh, actually, what did we do? We do GPU. Still showing. All right, I'll have to fix that. But in our example, if I have a GPU, I have another slide later to show that. So here's an example of different ways you can configure your job script to use all the cores in memory. Example 1, this is the way max config will output the parameters, 1 node, 1 task per node, and 96 CPUs per task, and all the memory 488G. If you're using an MPI job and you need 96 tasks per node, and each one of those tasks uses 1 CPU, then you would want to switch these two values in tasks per node and CPUs per task. So just be aware, based on how your MPI, you want your MPI jobs to run, whether you should use 1 task and 96 CPUs or 96 tasks and 1 CPU. Here's another way you can specify in tasks. If you specify in task, you'll want to also specify, let Slurm know with some other parameter how many nodes you want to use. And in this case, you're using 1 node and 96 CPUs per task. All right, example 4, if you're not using nodes, you can just say in tasks is 96 and the number of nodes is 1. Slurm knows that you want to use all the tasks, all the CPUs on one node. So in task defaults to one core, so you're basically using 96 cores on one node. If you use in task per node instead of nodes, then you can use in task of 96, for example, and in task per node of 96. So now Slurm knows you only want to use one node. All right, this is not a way you should configure your job scripts, where you just specify in tasks and do not specify nodes or in task per node. What will happen here is your job will be scheduled across multiple nodes. If your software only supports running on one node, and you run this and you configure your job script like this, then the Slurm will create your job across multiple nodes, and then your software is only running on one node, and the other nodes are idle for the duration of your job. So be aware that if you specify in tasks, you need to specify nodes or in tasks per node. All right, single node job. Be aware of the software. Look at the help documentation for the software. Look for options like threads or CPUs. This will let you know that the software does support multiple threads. Sometimes some of the software, I've seen few software that's configured to just query how many nodes, how many cores are on the system, and use all of the cores. So if there is a way to specify cores, make sure that the software doesn't just query the system and use all the cores. And if it does, make sure you specify how many threads if you've configured your JavaScript to use fewer than the maximum number of cores. We also have a tool called tamulauncher. This is a way you can take hundreds or thousands of single core commands run a single job, and this job will distribute each of these commands across one or more nodes. So in task, again, this is basically what I said earlier. Make sure you use nodes or in task per node. Okay, we went over GPU avail and max config. In this example, if you wanted to use, if you look in the availability box here, the node AC046, there's two H100 GPUs on this node. One of them is available, so there is a job using the other H100, and it also shows you how much memory and how many CPUs are available. So you can configure your job script specifically to launch on this node. You can request the other 48 CPUs and 244 gigabytes of memory, and most likely Slurm will schedule it on this node. In this case, this AC055 is open, all of the cores and all the memory are available. Also, if there are two GPUs attached to a node, unless your software requires all of the memory and all the cores, just scale down the memory and cores to the number of GPUs you're requesting and the number of GPUs available. For example, if you're only using one H100 and the node has two H100s, then you don't want to schedule all the memory and all the cores, because then that ties up the entire compute node with your job, and the other GPU that's not allocated for your job is unavailable for other jobs because there are no cores and memory available. So you can divide your cores and memory in half if you're using one out of two available or configured H100 GPUs, so that someone else can use the other GPU. And if you do run out of memory, if your software does require more than the 244 gigabytes of memory, then you can go back and bump it up to 488 gigabytes and use the entire compute node. Also be aware that whether your software supports running on one GPU or multiple GPUs. All right, we went over max config. Here's what it looks like for H100. It actually shows you the config here for H100. I'll have to see what the bug is here while it's showing in PVC, but it shows you the maximum. In this case, at this point, when this was run, there's a maximum of 4. Actually, there should be a 4 up here. This number can change, of course, because it's a composable cluster. So this actually, I probably typed this in and didn't copy the entire bottom part here. So that's why you don't see a H104. I have to correct that slide. All right, so 2 types of GPUs. You can, as we mentioned earlier, the last part of the GRES parameter is the number of GPUs. This can be 1 to a maximum that are configured. And this is just showing you how this GRES parameter fits into your job script. All right, single node multi-core job script. So this is a single node. Nodes are 1 using 48 cores, 244 gigabytes. So you're only using half of this compute node. You'll also want to make sure whatever the number of CPUs that you request in the Slurm parameters, that you match the CPU with the options for your software. For example, threads 48. This is what you specified up here. If you specify CPUs for task 1 and threads 96, you're going to most likely overload the compute node, and your job's going to take even longer, and also the other jobs that are running on that node will take even longer. So make sure you match these values. Here's another example of matching the values. There is a environment variable called Slurm CPUs per task. So if you're using this multiple times within your job script, instead of hard coding 96 throughout your job script, you can just use this variable. So anytime you change this variable in your parameters, this variable gets updated and within your job script. All right, multiple nodes. Again, make sure your software supports multiple nodes. You can increase the number of nodes with the nodes parameter. These are just different options. If you do nodes, you can do in tasks per node, or you can do in tasks 192, for example. This is for 2 nodes. Just based on how you, what makes it easier for you, either to use in tasks per node or multiply number of tasks and then divide it by the number of nodes. Make sure it's not more than 96. All right, and then you can just increase the number of nodes. Your software may do well on 1 or 2 nodes, but when you reach 10 nodes, it may not scale up to 10 nodes. It may be the maximum recommended number of nodes for a piece of software is specified in their documentation somewhere. You can test it also. Just run it on multiple nodes and increase the number to run multiple job runs and then see what works best. All right, tamulauncher. There are sometimes when you have a lot of commands, and let's just say you have 1,000 commands you want to run, and instead of creating 1,000 jobs, you can run 1 job, and this job will handle 1,000 commands. Scheduling 1,000 jobs and launching 1,000 jobs all at once can overload the Slurm scheduler, and then can lead to this socket timeout error, which you may have experienced, or maybe not so much on ACES, but our other clusters we have. The Slurm scheduler gets overloaded because there's so many jobs scheduled at the same, within a minute span. All right, so tamulauncher, schedule your job. You have a commands file. This commands file has each of the commands. I'll show you that in a minute. You can also check the status of your job, and if your job that you scheduled runs out of time and it only completed 500 out of 1,000 jobs, then you can just run your job script again, and it will pick up from where it left off. All right, so let's just say in the left box here, these are all of your commands. You're running the spades application, and you're running one thread per command. All of these commands are different. You want to make sure your output files are not overlapping each other. Notice that this actually is an output directory, or it could be an output prefix. And make sure all these are different, so you're not so each of these processes are not trying to write to the same file. So you'll have a commands file with all of your commands in there. And then you have your job script. So your job script, you'll configure that based on how many nodes you want to use, how many tasks per node, CPUs per task. Each of these tasks is using one CPU or one thread. Put your module purge in there, load your modules, and then you run the tamulauncher command and just provide the name of your text file. And the name of the text file can be anything you want. You can call it commands-in, command.in, commands.txt. Okay, so you make sure you load the software modules in the job script, not in your commands file. All right, if you were to configure each of the, you can configure your commands to use more than one CPU or more than one thread. You would just need to change this to match what you have in your commands file. So each task is going to use 4 CPUs, and then you'll reflect this in the way you configure your job script. All right, we're going to practice creating one of these commands files. It may not be, you may not ever use this, but there are some useful Unix commands that you can learn from this. And if you do run into a case where you need to create 5, 10, 50, 100 commands, or for whatever reason, then this may be easier than going to an Excel spreadsheet and trying to create these commands and then copy and paste and exporting back over to the cluster. So let's follow along. So first we're going to go to our scratch directory. You can see which directory, pwd. And then you can copy and paste this, make directory seeks. If you have a copy of the slides, we posted a link in the chat. So just copy this. I'm going to go back. I'm going to copy this. No, paste copy worked too well here. Paste didn't work here in my browser, so I'm going to just type that in. So this is just going to make a directory, create empty files that we can use. So first I'm making a directory called seeks, and then the touch command creates a file. Each of these files is in the seeks directory. It's called S1, R1 fastq, all the way to S40, R2 fastq. Okay, I already have a directory called seeks. I already have a directory that's already been created from last time. I'll just remove it, get it again. All right, so that created it. So now I've got a lot of blank files. These are example input files where sample one has two files, R1 and R2. So two files go with sample one. And so what we're going to do is create some commands using, we need to get the sample name so that we can use this in the commands. So let's do the first one, file. File is this is a variable we're going to create. S1, auto1, and I just hit tab to because that file exists. All right. So to create a variable, you just use the name of the variable without the $sign, and to see what's in the variable, you can say echo with the variable with the $sign. Just be aware that you want to make sure that this is not this variable is not overriding an environment variable. So use lowercase for your variables. And then we see set the variable, and this is what's in the variable. Now you can use another Unix command called base name and just give it the variable. And what base name will do is it will strip off all of the path, whether it's all the relative or absolute path from your file, and just give you the file name. All right, so now we want to capture that into a variable. So we're going to call this variable sample. Sample equals, okay, this is when you say $, open parentheses, this means you're going to run a command and capture the output into the variable called sample. Base name file. All right, so $ parentheses, this means you're running a command and capturing it in the sample variable. All right, there's no errors there, so now we have a variable called sample. It's going to be in this environment. As long as I have the environment, this window open. If I was to log into a new session, this variable sample is not going to be in the other session. So we're going to use this sample variable, and we're going to capture the S1 out of there. So let's use another useful Unix command, and what we will do is strip off the r1.getGZ, strip off the r1 squeue.gz. Squeue. All right. So I stripped off the end part here. You could have copied this and pasted it. Copying from that PDF didn't work, but you can copy and paste from here. If you double click and then you pick Control V and paste. Okay, so anyway, S1, this is the sample name. So over here, we've captured the sample name. We stripped off the R1 FASTQ. Now we just have the sample name, which is going to be S1. So also you want to make sure you match as much as possible, so you don't strip off this 3. You want to capture sample 13. All right. The next one is running a for loop. So you just type in, you just start typing in for. So file is a variable. It already has a value in it, but by running it again, you're going to assign a new value to this. Star _r1 dot star gz. So we're just going to capture the files that have R1 in it, because if we capture all of them, then we're going to have the sample name twice. So we only need it once. So we're just going to capture that's going to have an R1 there. And when you hit enter, you're going to continue this loop until you type in the done command. So the next line is do read1 equals file. So we're creating a variable called read1. Read2 equals read1. And we're going to substitute. This is a little different than the first one. The first time we went over this, we stripped off part of the variable. Now we're going to actually make a substitution on parts of the variable. And the part we're going to substitute is R1 dot. We're going to substitute this with R2 dot, because this is the second file. All right. And then we're going to do equals $. There's the base name command, and I need to use a parentheses here. Base name for read1. And then finally, once you get all your variables created, you can echo the command -1, 1, -2. So the -1 and -2, these are options for the spades command. So I'm actually using this braces here. So I'm taking the variable sample, whatever's in the variable sample, and I'm appending _out to the value. So if you want to append the value to a variable, you can put the variable in braces like this. If I did it like this, this says there's a variable called sample out, which we didn't create that. So make sure you have that. Threads 1, done. So you can see we created a lot of commands, and you can see each of these commands has the output file, the number of threads. We could have set that to 4. And if you want to, you just hit up arrow, and there's your command. And then you can save, you can use the redirect operator to put it into a file. All right. Now, well, so we have a file called command. Commands.txt. Okay, this just shows you the size, and you can see the top few lines of txt. All right, so we covered some useful Unix commands, such as creating variables, using the base name command, or stripping off characters inside the variable, or replacing characters in the variable. So I didn't go over this. I skipped that line, but this is replacing when you use a /, a value, a / in another string. You're replacing the R1 with R2 inside the sample variable. All right. That can be useful at times, and if you learn these commands, you can use these for other purposes. So they're very useful. There's another way, a more complex way. If the names of your files are not consistent in the way you want to capture the sample name. For example, this is sample 2 S2. This is sample 3 S3. So you can't just strip off R1 fast Q. You need to also strip off this S3. So then this is, I mainly use this for reference. And if I ever need to use this, I'll come back to this slide. Sometimes I'll just type this in and see if it works. But most of the time I'll come back to this slide for reference. But if you ever run into a case where you need to strip off part of a file name, for example, that's not the same across all your file names, then you can use these commands. Basically what this means, if you take the variable, for example, sample was the name of the variable, and you do #* and then you do R1, for example, as a substring, this will drop the beginning of the variable up to the first occurrence of the substring. If you 2 pounds and an asterisk will drop the beginning of the value up to the last substring, last occurrence. So you might have multiple underscores, and you want to only remove everything after the first underscore, or you want to remove everything after the last underscore. This actually will drop the part of the variable from the last occurrence to the end, and then from the first occurrence to the end. So there's 4 different ways you can use this. So what we're going to do is we're going to take a 10-minute break here, and then you can work on this. And if you have any questions, you can ask when we come back. So we're going to come back at 2:50. So we'll take 11-minute break, 10-minute break, and basically you can just type in the command, and here's the output of what you should see when you type this in. So if you have any questions, post them in the chat, or if you want to unmute yourself and ask, you can do that. But we'll take a 10-minute break and be back at 2:50. Okay, let's continue. I just want to make a couple of comments here. So earlier, when I was going over this slide, it says to configure H100 with 4, but there's not a H100 4 up here. This is just where I copied and pasted the latest configuration up here, but didn't update my parameters. If you do run this, this will show H102 because there's only H100, 2 H100s. Next time I'll just make sure I have to copy all of this. And also the max config, I did max config GPU, and I was expecting it to give me the H100 because that's the GPU, but actually the default in the GPU queue is the PVC. The default is the GPU that has the highest number of nodes. So there are 17 nodes that have PVCs. So the default for the GPU queue, at least for the max config command, is showing PVCs. If we had 18 H100s, then the default for the max config dash partition GPU would be the H100. So this is correct. This is correct. The max for the GPU partition is the PVC 8. And if you wanted to specify the type of GPU, then you would specify H100. And this shows you the maximum H100 config is 8. You can see up here that it is 8. All right. So really the bug I had was in the slide. I should have copied and pasted the entire thing instead of just the configuration. All right. So let's go back here. All right. So useful Slurm runtime environment variables. These are variables you cannot see on the login node. They're only available once you submit a job. So tempdir, all caps like this. This is a NVMe drive on the compute node, is directly attached to the compute node. It has 1.4 terabytes of available space. If you have software that's writing thousands and thousands of temporary files, and you can specify a temp directory, then it would actually, or most likely, speed up your processing, since you're writing directly to a drive that's connected to the motherboard instead of writing to a drive that's connected across the network, a shared network where a lot of other people are writing files. So if you request the entire compute node, and this temp drive 1.4 terabytes is available for your job. For an example, if the software does support a temporary directory, in this case, the samtools command, when you're sorting, you can specify a temp directory, and this is how you would use it in your commands. Use this environment variable. This directory is created, the value of this variable is created at runtime, and it's the name of, it includes the name of the, includes your job ID and the name of the temp directory. And then when your job is complete, that temp directory gets deleted. So anything that you wrote to that temp directory is gone when your job is completed. If you need anything in the temp directory, you'll need to copy it at the end of your script, or if it's critical and you don't want to lose it, then for example, if you're running checkpoints, then you don't want to use the temp directory. We went over the Slurm CPUs per task. You can use this variable instead of hard coding the tasks in your commands. Array task ID, if you use the job array, there's a task IDs. Slurm job name, you can use this if you're want to create output files with the job name. That's taken from the job name dispatch parameter. There's a node list. Some software you need to specify the node list, pass this, the value, the names of the nodes that are running to the software. So you can get this value using this environment variable. And the job ID, this is very important. If you have any job failures, send us the job ID. We can get a lot of the information we need from just looking at the job ID. These are Unix environment variables that you can use. User, if you need to if you need to use your username for anything as a variable. Scratch directory, this scratch, anyone can type in the $scratch directory, and that value is set differently for everyone. That is their scratch directory. This is my username, scratch user. All right. And then OMP num thread, sometimes some software can utilize this OMP num threads variable. By default, it's set to 1. If your software, read the software manual, and if it says you need to specify the number of cores using this environment variable, you can do it by exporting this variable before you run your commands. And there's a PWD variable if you need to use that. All right, so what we're going to do now is we're going to submit a job, and we have an application called GCA templates. So this GCA templates has a number of example job scripts that you can run. The job scripts are configured with example data, example commands, example SBatch parameters, all configured. So really all you need to do is just submit the job. And this, so if you want to understand how the jobs are running, you can submit it once, understand how the job script works, and then you can replace the input files and update the SBatch parameters and any of the software options with values that will be required for processing your input files. So let's work on this. All right, so make directory, learn class. Oh, I spelled scratch wrong. SC. I already have this learn class. All right. Let me start that over. I'm going to do this. I don't like using a full path in my. Okay. Scratch Slurm class, CD. All right. There's nothing there. You can see our directory. You can just type in GCAT and hit tab, and it will complete the command for you. And then you'll get this menu, and we don't have a lot of templates on ACES right now, but we do have some useful ones. So what we're going to do is enter number 1, because we're going to use the category of fast queue files. And then you can continue through the menus until you find BBMap. There's only one option here, error correct and normalize. This is for sequencing data, DNA sequencing data. So we're going to, that's the task we're going to use. If this task had multiple software versions and we had a template for each of these, you would be able to select the version. Sometimes the command changes across versions. Sometimes it's the same. But in this case, we only have one version, and this is sometimes you have what's called a singled-in library. Sometimes you have paired-in library options. In this case, there's only one option that we have in our example script. So there's only one value you can select. And then it says you want to copy this script. The script name is run BBMap. Tells you the version of the BBMap you're running, and it tells you kind of like an option that's configured in this script, and it also lets you know what cluster this is configured for. So yes, we want to copy that. Okay, and then it also reminds you that this is just an example template script. You will need to update it with your input files. You'll also want to change any SBatch parameters for mainly the runtime. You'll want to increase the runtime as needed in case this is a smaller data set. If you have a larger data set, you'll definitely want to increase the runtime. And then search for newer versions. Look on the web. Look on the software website. Also, you can use the module spider command. See if we have a newer version of the software, but we just don't have a newer version template script for that software. Most of the time, you can just change the version in the template and change the name of the module, and it would work. Sometimes they change or they require different options. All right. So we're going to submit this command as SBatch, and then you can type in RUN and hit tab, and it'll complete that for you, so you don't have to make sure you don't miss any dots or dashes. And then it's going to say your job submitting was using your default account. Your account balance is 1,000. Your job ID number is 241674. So you can use SQUE-UE. Let me make this full screen. So I've actually got 2 jobs running. I submitted 1 job. These numbers are sequential, so whoever submits a job after me is going to be 241675, 241676, 241677, like that. So I submitted this job a while back. Actually, it was from the directory I deleted, so I'm going to cancel that job because that I want it running in this directory I created. So cancel a job. Use the scancel command. You don't have to do this unless you want to cancel the job. All right. So now I've only got this one command, this one job I just submitted. Okay, so notice that my job, there's a couple different ways to see how many CPUs are requested. You can see right here, the number of CPUs is 96 and 1. You can also I just look inside the job tree. I'm using the last command to print to the screen 1 page at a time, and you can see that I've configured this. I know this BBMap software can use all 96 cores, and your job will complete quicker if you put 96 instead of 1 core. Don't worry about trying to save service units, but use the entire node to get the job done quicker. I've also included this job stats command, and I'll show you what job stats is, and that's a way to monitor resource usage. And when I say resource, I mean monitor the percent CPU load and the amount of memory that's used throughout the job. At the time I created this job script, the maximum amount available was 480. Now you'll see 488, but that's why this is 480. I'm hit Q to quit. And you can see I submitted that other job. I did not have there's not a submit time here. Actually, I'll show you another way to see the submit time. But notice it says start time. This is like the 17th. That's like 7 days from now. The reason for that is the CPU queue has a maximum runtime of 7 days. So as far as Slurm knows, all these it might take 7 days before if all the jobs that are running in the CPU partition run exactly the maximum 7 days, then your job's not going to start until the 17th. But a lot of jobs are going to complete sooner than 7 days. So this isn't the actual start time. It's probably the maximum start time. And I submitted this first job 421241455 probably about noon. So actually it's going to take more than a few hours for your job to launch. So let's just let that sit there and we'll go over some things here. So monitor a running job. You can actually run S control on a pending job. So show job. I double click that and I hit Control V. So S control show job shows you details about your job. This seems kind of neat at first, but I never really used this. You may want to put this at the end of your job script so you can capture this information. But a lot of this information you can capture with different commands. This information will not be available once the job is complete, whether it fails or it completed successfully. It will only work for a few minutes after your job is done. So you can capture it at runtime at the end of your job script, or if you don't really, you can get this information in a different way, and I'll show you how to do that. This is just an example of the output based on this SBatch parameters. All right, SEFF. This is a way to see. This is a Slurm command that shows you how much of the resources were used at runtime. This command is accurate if you select only half of the compute node. Half of the cores on the compute node. Then the CPU efficiency is based on the number of cores you selected, and the memory is based on the amount of memory you selected. So you can run SEFF for your job ID. It's not going to work right now because your job's running, and it's going to tell you efficiency it's not available because your job hasn't run yet. I have run this before, so job 5430. Now I can see the job was completed. I used 96 cores. This is the time across all 96 cores. So really what you want to look at is this percent efficiency. So it's about 47% of the core time. This is actually the amount of time, wall clock time it took. It only took 4 minutes and 29 seconds to complete this. And the amount of memory used is 184 gigabytes. So it only used about 40% of the entire compute node. So this information is there. It'll be available even long time after the job is complete. This is stored in the Slurm database. All right, so I mentioned the job stats command. Here's a link to the page. Basically what you do is after you load your modules, put the job stats command with an ampersand to send it to the background, right before all of your commands, and in the very last line, you can put job stats on there without the ampersand. Don't put the ampersand here because this sent it to the background. And you only want to send it to the background right here. So once your job script completes, these commands will end, even though it's running in the background. Slurm will stop all background commands. But while this is running in the background, this first command, it's creating a log file. It's querying the amount of memory used and the percent CPU load every 10 seconds. And then it creates a log file. And then when your job is complete, you run this command again, and this job sets will recognize that there's a log file here, and it will create a graph. So this is what a graph looks like for a GPU job. There's a separate graph for the CPU load, which we'll see in a little bit. So, but in this example, this job script requested 2 H100s in the parameters here. And if you look at this, the H100 was idle for about 10 hours, and then there was some activity. And I actually ran, this is actually looped through the same command 3 times. So there was another period of the GPU was idle, and then there was some activity, and then the same way here. So actually what we can see that there was activity on the GPU. If you're not sure whether the GPU is being used, you can run this add this job stats command to your job script, and you'll get a graph like this. This will create a graph for each GPU that's attached to the job. This job is configured with 2 GPUs. If you configured it with 1 GPU, it would only create 1 graph. In this case, the second GPU has no activity to the duration of your job. So this GPU was idle for almost 30 hours. Then no one could use the other GPU for 30 hours because the software does not support running on 2 GPUs. So be aware of how many GPUs the software supports, and don't leave these H100s idle for in this case, over a day, because we have a few of them, and everyone, they're in high demand. All right. So the service unit calculations, we saw that when we submitted the job, it gave us the number of, actually it didn't print the number of service units required for that job. Right now we haven't enabled the job Slurm to subtract the number of service units from the job submitted. Well, that's in the near future, but for now we have a count set up, and what you will see is the number of service units that were required to start this job. So let's say your balance is 1,000, and it costs you 500 service units to start your job, and your job completes in half the amount of time you configured it for. Then you will be reimbursed for half of the service units that it costs to launch that job. All right, but right now we don't have charging enabled, but we do have accounting set up. So each of the this is an example. Let me go over this first. So if you request 1 core and 5 gigabytes of memory, for 1 hour, you are charged 1 service unit. If you request 1 core and 6 gigabytes of memory, you will be charged 2 service units per hour, because there's a chunk of memory that goes with a single core, and that's 5 gigabytes on ACES. So when you get into the next chunk of 5 gigabytes, you get charged a second service unit. If you configure 1 core and all the memory, you will be charged for all cores. So if you need to use all the memory or all the cores, you might as well just use the entire compute node, because you're going to be charged for all the cores on them either way. In most cases, the reason why you use HPC is because you want to use the maximum number of cores or memory. So this would be ideal to get a job completed quicker. But for accelerators, this is just a charge for the cores and memory. Each accelerator will have an additional service unit charge per hour. So the H100s are going to cost more service units per hour than the A30s. So be aware of that. All right, so I'll go over the dashboard. You can browse through the dashboard, we have a lot of utilities there. We have the dash or the portal. We have a lot of utilities. One is the dashboard. This is a place where you can request software to be installed. You can also create a help desk ticket or request a quota increase. We also have a way to manage your groups. If you're part of a group or you want to be part of a group, you can request it with that tab. All right, debug your job. If you get an error like this, CPU count per node cannot be satisfied. Just read the message and look at your job script, and you can probably determine that you may have configured 200 CPUs per node, but we don't have any compute nodes that have 200 CPUs. So best bet will say we don't have any nodes. Basically, it's telling you that we don't have nodes that match the CPU count that you requested. All right, pending jobs. We do have scheduled maintenances, but we do have a way that you can tell if there is a maintenance. If there is a maintenance or the cluster will be down, you can run the maintenance command. Currently, we don't have an ACES maintenance scheduled. If there is a maintenance scheduled, it will let you know the countdown to when the maintenance begins. In this example, the ACES maintenance will start in 3 days, 16 hours, 41 minutes. Okay, if you schedule a job for 4 days, it will not launch until the maintenance is complete and the server's back up, because you've scheduled it longer than the amount of time available before the maintenance begins. So that's what I've said here. 7-day job. You configured it before when this is the output, it will not start. So you can, if you schedule your job as pending, you can check the maintenance, see if there's a maintenance available or coming up. And if you scheduled it for 5 days and the maintenance is in 3 days, you can cancel your job and then you can reschedule it for 3 days and 16 hours, for example. And then if the cluster is not busy, it will launch. But if it takes several hours for your job to start, then you actually the window of this is closed, and you'll have to make it even smaller. So you might get by with just 3 days. But we showed you ways to see how busy the cluster is. So sometimes it takes a little work to see how to schedule your job or why your job has been in the pending state for a while. All right, this is a common error: exceeded job memory limit at some point. This just means that you one of your commands has run out of memory. So you can configure your job script to run more memory and submit the job again. Sometimes you see out of disk space or no space left on device. Check your quota with the show quota command. This shows you how many files you're using in your quotas. When you're done with the project, create a TowerGZ package and download it from ACES and delete the source. Just make sure, verify that the download is complete and that all your files are there before you delete it from the cluster. You can also request a temporary increase in files and disk quota for your project. All right, my job command. This is another way to see once a job is completed. There are some statistics on your job stored by Slurm, which we can get with the my job command. It'll show you when your job was submitted, start time, end time. Let's just go to that. Here's an example of a job. You just basically run my job on the command line in the job ID. Actually, this is another error. I copy and paste. This shouldn't be. This job ID should match this. I just ran it again. This is actually from a different cluster. So actually the job, this 88 should be 128.181. But anyway, let's go back to here. So this is my job 5430. And you can see this was This job is completed successfully. It was in a CPU partition, one node. It gives you the node count and the number of CPUs that was requested. And you can see the efficiency, 47%. And you can see at this time when I submitted it, it took about 12 seconds to launch. And it ran for 4.5 hours. It used 184 gigabytes, which is about 40% of the 480 requested. And it also gives you where you submitted it from and the name of the command you used to submit it. And it also will let you know if the original JavaScript was changed or if it doesn't exist anymore. And this is helpful for us when we're debugging your jobs. If you just give us a job ID, we can get this information and help you debug that. All right. So on the portal, we have a number of interactive apps. These apps are mainly GUI apps, graphical user interface apps, such as RStudio or TensorBoard. If you have your own GUI application that you've downloaded and want to run, want to launch, you can use the VNC app. This will give you a command line on a compute node, and on the command line you can run your GUI application. So once you launch one of these jobs, they're interactive jobs. Let's just say, for example, Jupyter Notebook. You start a job, you can launch it on the entire compute node. When you're done, and once your job starts, you can go use the web to connect to that job, and then you can run your Jupyter Notebook. You can close your browser and go to a different computer and log in, and your interactive job is still running. When you're done with it, you can delete your job, and then you'll be reimbursed for the service units when service units are finally when charging is enabled. It's just good practice that when you're done with the interactive apps to cancel your job so you can release the nodes so other people can use them. All right. So this is just information about if you need help. We have a user guide, and we also have a lot of information on our what we call knowledge base. And if you can't find information you're looking for there, you can send us a message to our help desk. Just let us know which cluster, your job ID, which we can actually get your username from your job ID. We can get a lot of the other information from your job ID, but just give us information of how the error occurred and let us know when we resolve the issue, because we use a ticketing system and we can help you with that. So right now, these jobs are pending, but what you can do at a later time, check on when your job is finally completed. This job only takes about 5 minutes to complete. So whenever the job, we could probably have changed this to 10 minutes instead of an hour a day, and it may have launched sooner. I'll probably do that next time, change it to 10 minutes. Since I know it only took 4 minutes last time, and instead of a day, and it's not not requesting a GPU, so the GPU avail command wouldn't help you here. I could resubmit it. I could cancel this and resubmit it. I'm going to go ahead and cancel it. And then I'm going to modify this. If you use VI editor, you can use VI. I'm going to show you the editor here. So files, you can use the files application and go to your Scratch directory. So remember we went to Scratch, and then we went to Slurm class. And this is our job script. So I'm going to edit it here, edit. I'm going to change this, take away 1 day, and I'm going to put 10 minutes. And then click save. And then I'm just going to close this, the tab. Okay. Now, come back to our session here. So now you can see as it's been set to 10 minutes, queue to quit. I don't have any jobs running. I'll resubmit this job. Yep. Wrong command. S batch. Now it's still pending. It's still pending, but most likely reducing the time is going to, the job will launch sooner than if you requested an entire day. So if you want to make that change to your job script, you can do that. I did files in the portal, files. I went to my scratch directory, navigated to my Slurm class where I can see my file, and then I use this edit button. I think you can also do this. I think if you just click this, it might edit. Maybe I'd use it. Yeah, that's just to view it. So if you want to edit it, edit. Hit up arrow to see run your last command. Okay, so that's pretty much it. When that completes, you're going to see a number of files like standard error, standard out. That was the job ID. Let's navigate to this directory of a job that already completed, or I'll navigate and show you. So what you can do whenever your job is complete. You can actually view the images here. So let's do classes, Slurm class. So this is here's the name of the job script, and it created a number of files. There's some results files. This is the normalized files. Here is the images, PNG. There's a PNG file here. This is the CPU. This did not run on GPUs, so you're not going to get any GPU graphs. But if you configure a job script to run on GPUs, it will automatically create a GPU graph for you. So you can see the percent load. This is 100%, means all the CPUs. If all the CPUs were at 100%, then this red bar would be up here. But you only see about, maybe an average of about, I think that we saw 48% or 50%. So the duration of the job, you can see there are different processes over time. The percent of cores changed over time. Amount of memory that was used is in blue. This is actually system memory plus the job. System memory is about 10 gigabytes. So that's when it kind of starts to look. It doesn't start at 0 here. You can see that over time, the amount of memory used is increasing. This gives you an idea of what goes on during the span of the job. You can see this is minutes. Remember, the job took about 4 minutes. And this is actually the cache memory. This blue one is the actual memory that will be reported by Slurm in the memory utilization. Gives you a lot of information here of what the job ID is, in case you have this image and can't remember where you got it from. It also shows you how long the job ran and on which cluster it was used. So we'll hang out here for a few minutes, see if anyone has any questions about any of this. Otherwise, just check back, see when your job completed, and you'll see these files. And you can use the Files app in the portal to view the images. This is still loading. Oh, error occurred. Back to classes. Learn class. Okay, it reloaded. All right, so we'll hang out here for about 10 more minutes. In case anyone has any questions, you can put them in chat, or you can unmute yourself and ask. Otherwise, if you don't have any questions, you're welcome to leave. Thank you for attending. And again, if you have any questions for what we've gone, this is being recorded and we will have it on our YouTube channel once it's been processed. Otherwise, you can contact us using our help desk email, which is on our website. Thanks.